This video is dealing with logarithmic graphs to any base. So we'll look at base 2, base 10 and base e here first up. Logarithmic graphs are similar in some respects to exponential graphs. They contain one asymptote. One of the domain or the range is all the real numbers. The other one is the positive real numbers. We'll see that in a minute. But there's some similarities there because we know that exponential functions and logarithmic functions have that relationship, because we know that if we've got log e to the power of x to the base e equals a, then e to the power of a equals x. They have that sort of relationship. Alright, so let's start simply with the graph of log 2 to the base x. So I've drawn it here. You can see there's a couple of points that I've placed in here. One crucial point here is 1, 0, and that's because if you look at putting x there and replacing it with 1, okay, we would get log 1 to the base 2, and we know that log 1 to the base anything is always 0. So in all these graphs, when x is 1, okay, y equals 0, because log 1 to the base anything is always 0. And why is that? Because 2 to the power of 0 equals 1, if we take it from long form to index form. Okay, so it always passes through, unless it's been dilated or moved or something, the point 1, 0. Put in another point here, 2, 1, and that's because if x equals 2, log 2 to the base 2 is 1. If the base and the other number there are the same, we always know that that is a result of 1. So that's where we get the 2, 1 from. You'll notice that the domain is the positive real numbers. There's no negative domain here. That's because x cannot take on a negative value in the log. So there's the basic shape of log x to the base 2, and it's also got, and I haven't pointed this out yet, but it's got an asymptote of x equals 0. So the y-axis is the vertical asymptote on this occasion. Alright, log x to the base 10, similar graph, once again passing through 1, 0, and we've also got that point there, 10, 1, because of x is 10 in there. Log 10 to the base 10 equals 1. Asymptote is the y-axis once again. Log x to the base e, and this is the graph that we'll be focused on mostly here. Same again, intercept 1, 0, and I've got a point there, e, 1, because if x equals 1, if x equals e, log e to the base e equals 1. And position e where it is here, as you can see, at about 2.71, because the value of e is 2.71. Alright, let's move on and talk about the common features of these graphs. The graphs all cross the x-axis at 1, 0. That's because log 1 to the base a equals 0. Okay, we pointed that out before. The vertical asymptote is always the y-axis, or x equals 0, because log 0 to the base a is undefined. Okay. The domain, if we switch back here, the domain is all positive real numbers, and the range is all real numbers. Okay, so even though this looks like it's going to go and be asymptotic, it's not, right? We'll in fact keep on going and at both ends of this graph, so down here and over there, and we'll cover all the real numbers for y, for values of y. So the range is real, the domain is positive real numbers. And they're all increasing functions. If I get the gradient anywhere along this log graph, you can see it forms a positive gradient at any point there. So they're always increasing functions. Remember, functions that have positive gradients are what we call increasing functions. So they're the common features of log graphs, logarithmic graphs to any base. You can pause that if you like and take some notes. Dilations in the x-axis. As we saw with our previous graphs, the exponential graphs, the number out the front here gives us our dilation on the x-axis. You'll see that still common to all these graphs is that intercept there, 1, 0, that hasn't changed. Because if x equals 1, just my arrow happening here, if x equals 1 here, that means we get log 1 to the base e, which is 0. 2 times 0 is 0. So it doesn't matter what number you've got out the front there. The overall value is still going to be 0. So it's not going to change that intercept of 1, 0. But if from there on, things will change by having that coefficient. For example, let's take the point here, e, 2, which comes from this graph here. If x equals e, okay, so if x equals e, we're going to get log e to the base e, which is 1. 2 times 1 is 2. So if x is e, y equals 2. So what we have then is a dilation from the x-axis. Their original graph, the log x to the base e, so a 2 out in front takes it twice as far away from the x-axis. So dilation by a factor of 2 from the x-axis. A half out the front will take it closer to the x-axis, a dilation by a factor of a half from the x-axis. So they're the dilations in the x-axis, controlled by the coefficient of the log expression. Dilations in the y-axis, this is when we've got a number, a coefficient, in front of the x here, okay, and here, okay. Now this time we've got a dilation in the y-axis. You can see now my x-intercepts have changed. Before that was 1, 0. If I have a log a half x, which is the green graph, the intercept is now 2. That's because to create a situation now, if I look here, to create a situation of log 1 to the base e, x would have to be 2, because a half times 2 is 1. Log 1 to the base 0 log 1 to the base e is 0. So to create that intercept now, I need 2. So if x equals 2, y equals 0. And you can see my intercept has changed over here as well. So a 2 in front of the graph, 2 in front of the x, beg your pardon, dilates it closer to the y-axis. So here we're dilating, if we've got y equals log e, say, to the kx, our dilation will be by a factor of 1 over k from y-axis. So take this one for an example here. We've got a 2 in front of the x, so we've moved closer to the y-axis by a factor of a half. Okay. Here we've got a half x. Okay. We've moved by a factor of 2 from the y-axis. Okay, so 1 over a half. So the dilation factor here is by 1 over the coefficient of x. Vertical translation. If we've got a plus 1 tagged on to the log x to the base e, and be very careful, these two things, and I'll write them here, and please make note of this if you're taking notes. These two things are different. And that's why you should bracket the second one, alright? They're two different things. Don't get them confused. Here, it's sometimes better to write that one so you don't get confused as 1 plus log x to the base e. In any case, what these do, as you probably realise by now, is take the log x to the base e graph up by 1, a vertical translation, 1 place, so you can see the points have been taken up. If I pick any 2 points, it's taken up by 1 unit. Horizontal translations. Now this is where you've got the a plus 1 or a minus 1 in the bracket there. So it's log x plus 1 to the base e. Get that distinction from the previous one. And same deal again, guys. We've seen it so many times now. If we've got a plus 1, it moves the graph 1 place to the left. If we've got a minus 1, it moves it 1 place to the right. And you can see on the graph, the purple graph is a plus 1. So we've moved from the original, which is the black graph, one place that way. So the asymptote is now at, I should mark that in, is now at -1, okay? And all the points have been moved 1 unit to the left. Okay, you can see all those key points in the black graph to the purple, 1 unit to the left. The orange graph, okay, is a -1, so it's been moved 1 unit to the right. So all points have been moved 1 unit to the right, including, of course, the asymptote. I might just get rid of all the arrows that I've just drawn now, just so you can see that clearly once again. There we go. +1 in the brackets, 1 unit to the left, -1 in the brackets, 1 unit to the right. Then we've got reflections. In, first of all, the x-axis. If the negative is out the front of the log expression there, it reflects it in the x-axis. And you can see there the points have been reflected to the other side of the x-axis. If the negative is in front of the x, so you can see here, it's log -x to the base c, we get a reflection in the y-axis, whereby points are mirrored on the other side of the y-axis, like so. Note how the asymptote hasn't changed. Okay, so that gives you a bit of background on logarithmic graphs to any base. Next video we'll go on and do a few problems.